Okay. Hey guys. So I've been called away from campus again. I apologize. But you have Jordan and Lindsay there with you today, and they are awesome individuals who are also teaching this class. They're both grad students who are very interested in mathematics education. That is their work, and so they will be super helpful. They've been actually tutoring this particular course for a couple of semesters now, so they're very well versed in what's expected and that kind of thing. So lean on them. Watch the video, do the work. You're going to be great. And then we'll get back together on Wednesday. What I want to do today is I want to kind of remind us of the functions that are belonging to this ITEC versus Dynasystems problem in Investigation 2 of Module 4. Section 6, which is the slides that I'm using here, didn't get quite as far as the first class of the day yesterday, and I wasn't as efficient as I was later in the day. So we're going to start with their slides so that we can get everything taken care of. And then we're going to move into Investigation 3 and talk a little bit about the formation of an exponential equation or an exponential function. And then what I'm going to ask you to do is to do a little bit of work on your own to turn in as prep work for Wednesday morning. So here's what I'd like to have happen. I would like to start with this ITEC versus Dynasystems things. If you recall in class, we talked about the fact that the ITEC device does not have a constant rate of change. In fact, it has a decreasing change as the years go by. And we talked about the fact that the reason for that is because whereas the Dynasystems device over here decreases exactly $45 for every passing year, giving us this constant rate of change and this linear pattern, the ITEC device is losing 30% of its value every year, meaning it's only maintaining 70% of its value, causing for a decreasing change in the value, meaning that with each passing year, we're taking 70% of a smaller and smaller chunk, and we're losing 30% of a smaller and smaller chunk, making that change reduce at a reduced rate. So let's talk a little bit about the functions. At the end of class, I asked Section 6 to do this, and the other sections had actually already accomplished this by the end of class. But I want to talk about these equations. We were supposed to define a function that models the resale value in dollars for each device as functions of the number of years from now, which was t there. So we have n equals g of t, where g of t follows what rule? G of t is actually the easier one to start with, which is why I'm starting there. Because it's a linear model, we know it has an initial value of 300 and it reduces by $45 each passing year. Now, the second part down here asks us to consider what the different pieces of this model represents. So if we say n equals g of t, which is the 300 minus 45t, we can start to think about what these different pieces represent here. In fact, let's do that. So we can say that the 300 represents the initial value. It's where we start. It's the y-intercept. It's when the time is 0, right? The negative 45 represents a constant rate of change, which is applied each year, or t. All right, so we've got this model here, which gives us what we need. Okay, so that's what that represents. On the other hand, if we tried to build f of t in the same way, if we were to, for example, say 300 minus, 90t, because 90 is what we lost in the first year, that would create a linear model that was much steeper than the Dynasystems model. And we know that's not true. We know that that model needs to lose less and less value every year. So we have to consider, what did we do to the 300 to get to that second year price? Well, we took that amount and we multiplied it by 0.7. And then for the next year, we multiplied that 300 times 0.7, which was 210. We multiplied that by 0.7 again. And then in the next year, we did it again and again and again. And so this idea of multiplying repeatedly, well, that's an exponential model. 0.7 times 0.7 times 0.7 is 0.7 cubed, right? Or 0.7 times 0.7 is 0.7 squared. So we've got this exponential model at play here. And so we end up with 300 times 0.7 raised to the t value. So let's take this guy and let's analyze its bits and pieces. And this is the part actually that that all three classes would really benefit from doing. So I want to start here with this, and I'd like for the other classes to make sure that they're paying attention to this as well. So we have S equals f of t, which is going to use the rule 300 times 0.7 raised to the t. In this particular case, what is the 300? Well, the 300 is still the initial value. And what does the 0.7 represent? Well, it represents the 70% of the value that still remains after each successive year. And so we're applying this 0.7 each year, right? So again, it's applied each year by multiplication. Whereas this guy right up here was applied each year by subtraction. You could technically say, actually take that back. We're going to say that's applied by addition, because we identified it as negative 45, and if we subtracted negative 45, that would be addition, right, which we don't want, and instead we're applying negative 45 by adding it on each year. So that kind of brings us to the end of the investigation 2 material. I feel like that's a good place for us to stop. So here's what I want you to do. I want you to take a moment. I want you to go to Module 4, Investigation 3, and go to problem number 1 and pause the video and consider these first 4 parts. Okay, now if you're in class with Jordan and or Lindsay, they're going to help you out with some of the stuff if you need to. You can work in groups. This is why I did not tell you that class was canceled today, is because I want you to engage with one another. I think a lot of you have begun to see the benefits of being able to work in groups, and so I really want you to be able to do that. So take some time, talk to each other, and see what you can do with this first problem here. This is the function f of x equals 2 to the x as an example of an exponential function, and some people call it the doubling function. If we allow x to vary and it increases by 1, what happens to the output of the function? So when the input increases by 1, what happens to the output? Okay, and then it's going to ask you the same kind of question in C and D. If we allow x to vary, the input, and it increases by 3, what happens to the output? If the input increases by 8, what happens to the output? So think about those things. Take a moment, pause, think about those things, and then come back. Okay? Now, hopefully you have done what I asked you to do. If the input varies by 1, increases by 1, the output should double, right? If we go from 2 to the first to 2 to the second, well, that's twice as much. If we go from 2 to the fourth to 2 to the fifth, again, that's twice as much, because 2 to the fourth is 16, 2 to the fifth is 32, and 32 is twice 16. So the output should double every time. Okay, so when x increases by 1, the new output is what percent of the previous output. Now this is a little sticky wicket here. A lot of students have difficulty with this, but consider this idea. We talked about this yesterday, this idea of percent change versus percent of. And what they're asking us here is the new output is what percent of the old output, right? So the new output is what percent of the previous output. So consider for just a second, let's just give ourselves a little table here. So I'm going to put in a little table down here. Okay, yanking down here. Let's just consider some input output here. So we've got x, and here we've got 2 to the x, whoops. So if x is, well, those are all weird. Let's try that. So we've got like, I don't know, maybe 0, 1, 2, 3, 4. Okay. And here, so 2 to the 0, remember, please, anything to the 0 power is 1. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. So when the input increases by 1, so from 0 to 1, what happens to the output? The output value, 2 is what percent of 1. 4 is what percent of 2, etc. So each of these is 200% of the previous value because it's the value itself plus another 100% of that value. So this is going to be 200% of the previous value, meaning that the percent change, okay, we talked about that difference, right? If the percent of is 200, then the percent change is an increase of 100%. Again, looking back at our table from yesterday, we can see the difference between percent change, right? So we had an increase of 215% here. There was a percent change of 215%, which meant that the new value was 315% of the old value. So, all right, sorry, I lost my place. So if we allow x to vary and it increases by 3, okay, let's look at our table down here, right? We go from 0, we increase by 1, 2, 3, or we start at 1 and we increase 1, 2, 3. The new output is what is how is it affected, right? So we could say that 8 is 8 times 1, right? Or we could say that 16 is 8 times 2, right? Because 8 is 2 cubed, right? And 1 is 2 to the 0 power. 16 is 2 to the 4th. And 2 is 2 to the 1st. So when I increase the input, right, the input goes from 0 to 3, right? The output increases by 8 times, right? Here we go. So what do you think would happen if we allowed the input to vary by 8? What would happen to the output of the function? Well, we could do some actual values, or we could start to think a little bit more abstractly, okay? We already said right up here that 8 is 2 cubed, and the input increased by 3, right? 8 is 2 cubed, right? It increased by 3. So it seems reasonable to assume that when the input increases by 8, the output should increase by 2 to the 8th. Oopsie. By 2 to the 8th power, which I don't know what that is off the top of my head, but 2 to the 8th power is, I think, somewhere in the neighborhood of like maybe 256. Is that right? Let's see, real quick. So it goes 2, 4, 8, 16, 32, 64, 128. Yeah, 256, which is about 256 here, which is exactly 256. In fact, let's say the new, because that's a little misleading. Let's talk about why I'm erasing that. It says the output should increase by 256. Well, that's not true. You don't add 256. You multiply by 256. So let's change that differently. The new output should be 2 to the 8th, or 256 times the old output. Yeah? Okay. That's more clear. So these questions, so again, vocabulary, right? The way we talk about things is important. And when we talk about something increasing by so much versus something being so many times as much, those have very different connotations. So let's keep that in mind, that the increase by assumes addition, right? It implies that we are adding, when in fact, that's not what we're doing in this doubling function. We just keep multiplying by 2. So we need to make sure our language goes with that. Okay, so what I want to do is I want to take a moment and look at some graphs. I want to start with 2 to the x, right? Here's 2 to the x. And we can look at some points. We know that 2 to the first power is 2, right? So there he is there. And that we know that 2 squared is 4. We know that 2 cubed is 8. There he is. We know that 2 to the fourth is 16. There he is, right? So we can see that on this right-hand side that things are moving up and they're moving pretty quickly. Exponential functions move really fast because all of a sudden you're not just doubling 2 and 4 and 8, you're doubling things like 128 and 256 and so on and so forth. On the right-hand side of the graph, though, the left-hand side of the graph, don't know my left from my right. I should be ashamed. I'm not. Okay. When I put in 2 to the negative 1, look what happens. 2 to the negative 1, boom, whoops, there he is 0.5. It's 1/2. Because remember that when I'm looking at 2 to the negative 1, right, if I look at, let's see if I can make this work. If I look at 2 to the negative 1, because we went to the right a minute ago, I've got 1 over 2. Remember that this negative exponent here, this is one of those places where the negative exponent means something different yet again. But 2 to the negative 2 is 1/2, right? Or we could say 2 to the negative 2 should be 1 over 2 squared, or 1/4. Just a little reminder there, right? That when we use a negative exponent, we are inverting that fraction when we use it numerically as an exponent, as opposed to this inverse notation, which we talked about last time, right? It's one of the things that kind of annoys me about mathematical notation. So we've got to the left over here, we've got this progression of 1/2, right? And then if we plug in, well, there he is. If we plug in negative 2, we should get to 1/4, right? If we plug in negative 3, we should get to 1/8. If we plug in negative 4, we should get to 1/16. And look what the graph is doing. It really looks like it's going to hit 0, right? If we move back over this way, it really feels like this is going to hit 0. But here's my question to you. Does it hit 0? When I was in calculus in college, my calc teacher, Dr. Purvine, had this example that he used. He said, picture a flea, and I don't like fleas because they're nasty. So instead, I'm going to say picture a frog. Picture a frog. We'll name him George. George knows English, and he can do what I ask him to do. So I say to him, George, I want you to jump halfway to the wall. I'm standing somewhere. I say, jump halfway to the wall, and he does that. And so I say, George, jump halfway to the wall again. And he does that. And then I keep saying, George, jump halfway to the wall. Will he ever actually reach the wall? Right? No, he's not going to reach the wall. Will it look like he's going to reach the wall? Will his nose be all but pressed against the wall? Yes, it will. So this kind of deceptive thing happens over to the left here. We approach 0, but we never actually hit it. And just a little foreshadowing, there's notation for that. And that notation looks something like this. We can say that the limit, as our input values approach negative infinity, as we put in bigger and bigger and bigger negative values for this function 2 to the x, it's going to approach 0. It's never actually going to get there, but it's going to get real close. And we'll talk more about that limit notation later in the semester, so you don't have to stress out about that too much. But let's see the difference here. So here's 2 to the x. Let's turn on 3 to the x. Right? What's going on with 3 to the x? Take a second and think about what's the difference between 2 to the x and 3 to the x. Pause if you need to. And then let's talk about 2/3 to the x. Boom. Oh, that was weird, right? That was different. And okay, what if we flip this fraction over? What if we call it, instead of 2/3 to the x, we call it 3/2 to the x? Well, boom, there it is, right? What I want you to do is I want you to think about this in your groups or on your own here in class. I want you to take a moment and pause the video. I want you to have some conversations about what's the difference between these 4 functions. What's really happening here? Take a moment and pause. Think about those things. All right, so with these four functions, right, what are some things that we can notice here? When we had 2 to the x, we know that it grows. This is exponential growth. Okay. But when we changed it from 2 to the x to 3 to the x, what we end up with is faster exponential growth. Because now instead of doubling every output, we are tripling every output, which means it's going to rise much more quickly. Oops. So what's the difference here? Well, instead of exponential growth, we have exponential decay, right? Of this exponential decay. It's no longer growing from left to right, it is decaying from left to right, because 2/3 is a small number, right? It's less than 1, which means that if I apply negative exponents to it, it's going to grow, and if I apply positive exponents to it, it's going to approach 0 to the right. So why is it that when I flip that fraction over, I get exponential growth again? And there's a general idea here that when the base is greater than 1, I have exponential growth. And when the base is less than 1, I have decay. Now, what is a base? Okay, so if I'm looking at an exponent, right? This 3/2 here, this 2/3, this 3, this 2, these are each the base of the exponential expression, and the exponent would be the x. Well, let's add a piece to this. Suppose I say instead of, and let's turn some of these off. We're going to turn off this one and this one and this one. Let's say that I add, so we've got some exponential growth here. What if I add a coefficient out in front? Just got some random coefficient. Let's call it, I don't know, 4. What just happened? What's the difference between this and this? Right? What is going on here? So every output, instead of just being 3/2 to the x, is now 4 times that much. So it makes it grow a little bit more quickly. But in particular, it also, look what happens on the y-axis here, right? Check out what's going on the y-axis here. If I delete this 4, I pass through the y-axis at 1. But if I add the 4 back, I pass through the x-axis at 4. Because anything to the 0 power is 1, so whatever coefficient is sitting out here in front is going to end up being our initial value. So if I adjust this a little bit, and I say that I want to look at this in a general sense, I want to look at f of x is equal to some coefficient times b raised to the x power. Well, let's talk about the jobs of these ideas. We already talked about it with the iTech device, and it's no different here. A is going to represent the initial value, right? Whereas B, the base here, represents the base of the exponential, which is also known as the growth factor. So back here, when we built this function, we could call 0.7 the growth factor of our exponential function. And if we talk about it back here, right here, we've got our growth factor. This guy right here is going to be the growth factor of an exponential function. So our growth factor is going to be revealed by this question of the new price is how many times the original. I put that on the wrong column at first. The new price is how many times the original. This is the growth factor right here in this column. So, but returning here to our functions, we can add in when B is greater than 1, the function grows. And when B is less than 1, the function decays. All right, so here's what I need you to do. For tomorrow, I'd like for you to take a look at Module 4, Investigation, what is this? Investigation 3, problem number 9. Specifically, I'd like for you to look at just problem number 9. You don't have to do number 10 as well, but the directions for all of 9 through 12 are right here on this slide, which is why I included them in the Dropbox. I want you to find the ratio of output values that correspond to increases of 1 in the input value. This value is the 1 unit growth or decay factor. So we're going to find that ratio of output values, find the growth factor. Determine the 1 unit percent change. So you're going to think about, okay, so if this is my growth factor, what's my percent change? You can look back at that table. And then part C says identify the initial value. What's the initial value when the input is 0? And then use that information to define a function formula for the relationship. So that's parts A, B, C, and D down below there. And that's what I'd like for you to turn in for prep work for Wednesday morning by 8 a.m. So thank you so much for watching the entire video and hanging out with Lindsay and Jordan. Please feel free to hang out and ask them any questions you might have. And I will see you in class tomorrow.